Welcome to the AWS Certified Cloud Practitioner Prepcast, where we guide you through everything you need to know for your certification exam. Whether you're just starting or looking to refine your knowledge, this course will set you up for success. Brought to you by baremetalcyber.com. Let's get started. One of the biggest challenges in modern application design is ensuring that systems remain resilient under changing conditions. Traffic to your applications may spike suddenly, servers may fail, or you may need to distribute requests across multiple resources. Elastic load balancing, or ELB, and autoscaling work together to address these challenges. ELB spreads traffic evenly across healthy resources, while autoscaling ensures there are always enough resources available to meet demand. For learners, think of ELB as the traffic officer directing cars onto multiple lanes, and autoscaling as the construction crew adding new lanes when traffic builds up and removing them when roads are quiet. Together they deliver elasticity, availability, and fault tolerance. AWS offers several types of load balancers, each suited to different workloads. The Application Load Balancer, or ALB, operates at Layer 7 of the OSI model, inspecting HTTP and HTTPS requests to make routing decisions based on paths or hosts. The Network Load Balancer, or NLB, functions at Layer 4, making it ideal for high-performance TCP and UDP traffic, where speed is critical. The Gateway Load Balancer, or GWLB, is designed to insert third-party security appliances like firewalls or intrusion detection systems into the traffic flow. Beginners should picture ALB as a smart receptionist who understands the details of each request, NLB as a fast turnstile that checks only tickets, and GWLB as the security scanner that all guests must pass through. Load balancers rely on listeners, target groups, and ports to function. A listener checks for incoming traffic on a specified port, such as HTTPS on port 443. Target groups define the resources behind the load balancer, such as EC2 instances, containers, or Lambda functions. The load balancer directs requests from the listener to healthy targets within a target group. For learners, it helps to think of a listener as the main entrance door, the target group as the group of clerks working inside, and the ports as the assigned desks. Together, they ensure requests reach the right worker. Health checks are a critical component of load balancing. Each target has to respond to health checks, often simple HTTP responses, to prove it is functioning. If a target fails its checks, the load balancer automatically stops sending it traffic until it recovers. Deregistration delay is an important concept. When a target is removed, the load balancer allows existing connections to finish gracefully before cutting it off. Beginners should see this as letting diners finish their meals before closing a restaurant table. Health checks and deregistration delays keep systems stable during changes. Cross-zone load balancing distributes traffic evenly across all availability zones, not just within one. Without it, you may risk imbalanced traffic if some zones have more targets than others. Enabling cross-zone balancing ensures that no single zone is overwhelmed, while others sit idle. For learners, this is like spreading out shoppers across all open registers in a supermarket, not just the ones closest to the entrance. Cross-zone balancing is a best practice for resilience and efficient resource usage. Application load balancers offer advanced routing features. Path-based routing allows different URLs like /images or /videos to go to different target groups. Host-based routing directs traffic based on domain names, like api.example.com versus shop.example.com. These features make ALBs flexible for microservices or multi-tenant architectures. Beginners should imagine a receptionist who listens to what customers say and directs them to the right department based on their needs. Routing by path or host enables smarter traffic distribution beyond simple load spreading. Sticky sessions, also called session affinity, are another ALB feature. They ensure a client's requests always go to the same back-end target. This can be helpful for stateful applications that don't store session data centrally, but it can also lead to uneven traffic distribution. Beginners should view this like a regular at a coffee shop who always visits the same barista. It builds consistency but may overload one barista while others are idle. The exam often stresses that sticky sessions should be avoided unless truly necessary, as they reduce flexibility. TLS termination is another role often delegated to load balancers. Instead of each target handling encryption and decryption, the load balancer can terminate TLS at the edge and then forward plain traffic to targets. This reduces the CPU load on back-end servers. Certificates for TLS termination can be managed through AWS Certificate Manager. Beginners should see this as security screening at a building entrance. Once visitors are checked, they can move freely inside. Offloading TLS makes back-end systems more efficient while maintaining secure entry. Security groups apply both to load balancers and to their targets. The load balancer's security group controls what traffic reaches it, while the target's groups control what traffic is accepted from the load balancer. Beginners should picture this as security checkpoints. The outer checkpoint verifies who may enter the property, while the inner checkpoint verifies who may enter the building itself. Both must be configured correctly to prevent exposure or blocked access. Auto-scaling groups, or ASGs, automate capacity management. They define a group of EC2 instances that scale up or down depending on demand. By maintaining minimum, maximum, and desired instance counts, ASGs ensure availability while optimizing cost. For learners, this is like hiring seasonal workers. When customer demand rises, more workers are added. When business is slow, the team shrinks. Autoscaling keeps applications elastic without requiring manual intervention. ASGs rely on launch templates or configurations, which define the instance type, Amazon machine image, networking, and other parameters for new instances. This ensures that every new server is built consistently. Beginners should think of launch templates as the recipe for every new worker in a factory. No matter when they join, they have the same tools and instructions. Templates guarantee uniformity across scaled instances. Scaling policies determine how ASGs adjust capacity. Target tracking scaling adds or removes instances to maintain a specific metric, like keeping CPU at 60%. Step scaling makes discrete adjustments when thresholds are crossed, while scheduled scaling adds capacity at known times, like increasing servers during business hours. Beginners should view target tracking as a thermostat maintaining steady temperature, step scaling as switching on extra fans when it gets hot, and scheduled scaling as preparing in advance for known busy periods. Warm pools improve responsiveness by keeping instances pre-initialized and ready to join the group quickly. This reduces the lag that normally occurs when scaling out. Graceful cooldowns prevent autoscaling from overreacting to temporary spikes by giving time for new instances to stabilize. Beginners should think of warm pools as having substitute players ready on the bench and cooldowns as taking a pause before adding more. These features make autoscaling smarter and less wasteful. Finally, health check integration between autoscaling and ELB ensures that only healthy instances remain in the group. If a load balancer detects a failing instance, autoscaling can terminate it and replace it with a fresh one. This creates a self-healing system where broken components are automatically removed and replaced. For learners, this is like a factory line where defective machines are swapped out before they disrupt production. Integration of health checks completes the cycle of resilience. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Elastic load balancers are not limited to EC2 backends. Application load balancers can route requests directly to AWS Lambda functions or containers running on ECS and EKS. This allows serverless and containerized workloads to benefit from the same intelligent traffic distribution used by traditional servers. Beginners should see this as a receptionist who doesn't just send visitors to human clerks, but also to automated kiosks or specialized service counters. By integrating with Lambda and containers, ALBs support modern architectures seamlessly, providing scalability and flexibility across diverse application models. Network load balancers are optimized for raw speed and are ideal for TCP and UDP traffic, including scenarios that require TLS pass-through. Unlike ALBs, which terminate TLS, an NLB can forward encrypted traffic directly to back-end targets without decryption. This is critical for workloads requiring end-to-end encryption or ultra-low latency. Beginners should view NLBs as toll booths that check tickets instantly and let vehicles pass without inspection. They don't interpret traffic deeply, but ensure it flows quickly and predictably, making them essential for performance-critical applications. Gateway load balancers address a unique challenge: inserting security appliances transparently into network traffic. These appliances might be third-party firewalls, intrusion detection systems, or deep packet inspection tools. Instead of configuring each connection individually, GWLB handles distribution and scaling of these appliances. Beginners should imagine GWLB as a security checkpoint on a highway where every car passes through inspection, regardless of which lane they use. This allows enterprises to insert advanced security tools into the cloud traffic path at scale, without custom routing complexity. Load balancers also support advanced deployment strategies like blue/green and canary releases. By assigning different versions of an application to separate target groups, traffic can be shifted gradually or instantly. For example, you might send 10% of traffic to a new version for testing before rolling it out fully. Beginners should picture this as opening a new checkout lane at a store and slowly directing customers there to confirm it works smoothly. Target group routing gives organizations safe, controlled ways to release new features without risking outages. Predictive scaling adds intelligence to autoscaling by analyzing historical trends and forecasting future demand. Instead of reacting only when metrics cross thresholds, predictive scaling can launch instances in advance of expected surges, such as daily traffic spikes. Beginners should think of this as preparing extra cashiers before the lunchtime rush begins. By staying ahead of demand, predictive scaling improves user experience while still maintaining cost efficiency, especially for workloads with well-understood patterns. Mixed instance policies in auto-scaling groups allow different EC2 instance types and purchasing options to be combined. For example, an ASG can balance between on-demand instances and spot instances, leveraging cost savings while ensuring availability. Beginners should view this as staffing a restaurant with both full-time and part-time employees. The mix reduces costs, but guarantees coverage. Spot interruptions may occur, but auto-scaling adapts by shifting to other resources, keeping systems resilient. High availability extends beyond availability zones into regions. Multi-AZ auto-scaling ensures workloads continue even if one zone experiences failure, while multi-region deployments provide protection against entire region outages. Beginners should see this as having restaurants in multiple neighborhoods or even cities. If one location closes, customers can still be served elsewhere. The exam often highlights this difference, testing whether you choose multi-AZ or multi-region strategies for resilience at the appropriate scale. Monitoring is a critical part of managing ELB and autoscaling. CloudWatch provides metrics such as request counts, latency, error rates, and instance health. Access logs from load balancers capture detailed request data for analysis. Beginners should think of this as a dashboard in a car that shows speed, fuel, and warning lights. Without monitoring, you are driving blind. Metrics and logs provide the visibility needed to tune scaling policies, troubleshoot issues, and demonstrate compliance. Costs must also be considered. Load balancers are billed based on usage metrics such as data processed and load balancer capacity units, or LCUs. Auto-scaling costs depend on the instances launched, instance type, size, and purchasing option drive expenses. Beginners should understand that scaling too aggressively can increase costs, while careful policies and spot usage reduce them. On the exam, cost awareness is often a subtle but important part of the correct answer, emphasizing efficiency alongside security and performance. Troubleshooting ELB and ASG involves interpreting codes and health states. A surge in 4xx errors indicates client-side problems such as invalid requests, while 5xx errors often point to back-end issues. Target health checks reveal whether instances are failing due to misconfiguration or overload. Beginners should think of this as listening to customer complaints. Are they caused by mistakes customers make or by problems inside the store? Correct diagnosis directs the right fix, and AWS's health data provides the evidence. Immutable deployments are a best practice with auto-scaling. Instead of updating instances in place, new ones are launched with the desired configuration, and old ones are gradually retired. This ensures consistency and reduces risk of drift. Beginners should view this as replacing old buses in a fleet with brand new ones, rather than repairing each bus while passengers are still on board. Immutable rollouts are safer and cleaner, especially in dynamic cloud environments. Stateful applications pose challenges for load balancing and scaling, since they often tie user sessions to specific servers. Resiliency patterns include externalizing state into databases or caches so sessions can move freely between targets. Beginners should imagine a locker system at a gym. Instead of leaving belongings with one trainer, members use lockers accessible from anywhere. This makes scaling and failover possible without losing user context, aligning applications with cloud-native principles. From an exam perspective, elastic load balancing and auto-scaling are central to availability. If the question asks how to spread traffic across multiple instances, the answer is ELB. If it asks how to automatically adjust capacity to demand, the answer is auto-scaling. If it involves resilience, self-healing, or scaling efficiency, both together are the right match. Beginners should be ready to identify when the scenario is about balancing requests versus scaling resources, two halves of the same solution. In conclusion, ELB and autoscaling provide the elasticity, fault tolerance, and safe release patterns that make AWS applications resilient. Load balancers distribute traffic intelligently, integrate with advanced routing, and manage TLS, while autoscaling keeps the right amount of capacity online, reacting to demand or predicting it. For learners, the message is clear. Pair ELB with autoscaling whenever you need both balance and elasticity. Together, they ensure systems scale gracefully, recover from failures, and evolve safely in production. That concludes today's episode of the AWS Certified Cloud Practitioner Prepcast. Be sure to tune in for the next episode and visit us online at baremetalcyber.com or cyberauthor.me for more resources, including news, mailing lists, YouTube videos, podcasts, and much more.